Okay, the next section, 7.4, is proving trigonometric identities. This is the section where there is very little math except for algebra, but everything is based off of logic. The better you understand how sine and cosine work in terms of their transformations, like we've gone over in 7.1, 7.2, and 7.3, and even some of the formulas and identities you've done in functions, the easier this section becomes. Now, unfortunately, because it's pure logic, there are no set steps for how to answer any given question. It's not like you can write down the things that you are given and look at what you need to find and, use a formula that is going to give you the answer at the end, or there are set steps. What we have to prove is that one equation is true. So we need to prove that sine 2x divided by 1 plus cos 2x is equal to tan x. Majority of your questions will be based off of that idea. Prove this identity to be true. So in order to prove an identity to be true, or to prove anything to be true, it needs to work for all cases. To prove something to be false, all you have to do is give one example, right? So it's important to remember that when you're proving something to be true, we cannot use examples. We cannot use values. We cannot plug in an angle like pi over 4 for theta and assume that that constitutes a proof. You can use that to disprove something. So for example, if I had sine of theta is equal to cosine of theta. We know this is not true. To disprove it, all I would have to do is sine of, let's say, pi over 3 and cosine of pi over 3. We know sine of pi over 3 is root 3 over 2, and cosine of pi over 3 is 1 over 2. So we can see that they're not equal. Yes, I could have done sine of pi over 4 equals cosine of pi over 4, and both of those are root 2 over 2. So I can give an example where it works. I can give an example where it doesn't work. But because there's one example for which it doesn't work, that is enough for that identity to be proven false. In order for it to be proven true, we cannot plug in a value like this, and because the answer is the same, therefore the whole identity must be the same. So what do? Let's go with this. Now, there are a few tips that we can remember, a few processes that we can remember in order to try to get a consistent process going. A few things like, do not go from one side to the other side unless you need to, and I would say majority of the times, like upwards of 95% of the time, you do not need to have anything switch sides. Simplify as much as possible. So for example, here I have sine 2x and cos 2x. Specifically, I have sine and cos. Here I have tan. So I'm going to simplify it. Instead of having sine, cos, and tan, I will change tan to sine over cos. Now I only have sine and cosine. Because in order to prove it to be true, I need the left side and the right side to look identical. That's the only way to prove that these two equations or these two expressions are equal to each other. So that's one part. Another process is to make sure you look at the big picture first. So for example, like I said, sine and cosine are the same, so let's go with that first. So sine 2x over 1 plus cos 2x is equal to sine x over cosine of x. Now, big picture, we have sine, cosine, and the 1. Now we start looking at what's different. Well, this has 2x and this has x. It is very difficult to turn sine x into sine 2x, but it's not very difficult to turn sine 2x into sine x and cos x because we have an equation for that. Sine 2x we know is 2 sine x cos x. The question you might be asking is, what's the point of that? Again, the point is I don't want the 2x here anymore. If I want to show that this equation turns into sine x and cos x, sine x over cos x, then I want to get rid of the 2x's here and here. Now, cos 2x has three different possibilities. Cos 2x can be cos squared x minus sine squared x. It can be 2 cos squared x minus 1. And it can be 1 minus 2 sine squared x. If I want to choose between these, I definitely would not go with cos squared x minus sine squared x, because in the denominator, I only want cosine of x, so I don't want to have cosine and sine. By that same reasoning, I would not choose 1 minus 2 sine squared x, right? Because I only want cosine in the denominator, which leaves me with 1 plus, and instead of cos 2x, I'm going to use this version, which is 2 cos squared x minus 1. Now, obviously, we need to simplify. 1 minus 1 cancels out. Then I have a 2 divided by 2. That's 1 and 1. So let's see what we have now. I have sine x, cos x at the top. In the denominator, I have just cos squared x. Well, cos squared x means cos x times cos x. So this cos x and one of these cos x's cancel out. And I'm left with sine x over cos x, which in this case now shows that the left side is equal to the right side. I have proven this identity to be true. A lot of these will take time. A lot of these will come across as very difficult. How to determine whether you've made a mistake? There's no set way. There's no easy way to find out if you've made a mistake. You can try to move up if you like, but my recommendation, if you end up in a situation where you're stuck, you need to go back, and if you can identify where you may have made a mistake, go for it. If you're not able to, then do not hesitate to just start here and take a different route, or go over the same route again so you can identify where the mistake may have happened. Proving identities is the most logic-based section that you will do in any section you'll cover in all of the Ontario Math curriculum. It can be a lot of fun if you're putting some time into it, and if you're enjoying the challenge. Some of these identities will be pretty tough. We'll go over them together in class as well, but I wanted to make sure that I give you an example of what it is you're going for. There isn't more that I can explain here. What I would recommend is sit down and practice.